have only kinetic energy. V naught is the periodic potential inside this material. So we have a structure, have some lattice, and there is a potential coming from all the atoms in this lattice. Is this potential V naught is periodic. And I have this term here, which is the spin orbit coupling generated by this electric field of the potential of the lattice. So I want to solve this equation, and I say it's a difficult equation because, well, first of all, I don't know what is V naught. I could know, but I would have to do some other calculation, first principle calculation to calculate this potential and consider all the atoms and have the lattice. But I want to avoid all of this. Okay, so I want to do something easy, that I can do some models, some things analytically, and I will start being fine with not knowing what exactly is V naught. And all this information of V naught, I will put it in some parameters, which then can be extracted from experiments. So that is the idea. So since the system is periodic, I can write the wave function in this way. So this is Bloch theorem, and this U and K is the periodic part of the Bloch function. So if I substitute this expression into this equation, I will get into this other equation, which you can see we have this extra term here, this K dot P, and that is what gives the name to this approximation. It's called K dot P because you have this extra term in the equation when you go from the psi to the periodic part of the Bloch function, so U. Now, what is the main idea of this K dot P approximation? It just assumes that you choose a K point, whatever K you want to choose. But you need to know what are these functions here for this point. So you assume that you know that at such a point, you know what the periodic part of the Bloch wave function of the Bloch functions look like, and then you use these states like a basis. Then you rewrite this Hamiltonian in this basis of a state at this K naught point, and then you solve the equation. So then you get the equation for a small k close, to this K naught. Maybe I can do an scheme here. Okay. So let's say that I have this my band, and I say that I choose my K naught here. So the first thing, I assume that I know what are the states at K naught, okay? I then build the matrix representation of this Hamiltonian in this basis that I know for K naught. So this is a basis here, and I use this basis to calculate this Hamiltonian in this basis. Now this Hamiltonian now depends on K, right? Then I solve this Hamiltonian for a different value of K. Let's say some value is K1. Then I solve I use the basis that I get for K1, write again the Hamiltonian in this K1 basis, and then solve it for another K. And in that way, I can move and reveal all the bands. That's what you would do, but this, you want to do this, you will need to do it numerically. So I won't do that. I just will calculate the band just close to some point. Okay, so I won't look at other Ks, but just close to this point. So what is this K naught point that you are going to choose? It depends. So you probably will like to choose something that is convenient. For the case of this in-plane semiconductor, so you can see the band structure that I show you. The most relevant things happen at this point here, when the conduction band have minimum and the valence have maximum. This occurs in these in-plane semiconductors at the center of the brilliant zone. It's a K equals 0 point. It's called the gamma point. So I will choose for this K naught, I will choose 0. And then, so you put K equals 0 here in this equation, so this K dot P terms goes away, right? And so, let me see here. Okay, a K equals 0, this goes away, this also goes away, this goes away, and I just then have H naught which is the kinetic energy plus the periodic potential and the spin orbit, okay? So I get this equation here. Now, in order to diagonalize this equation, I need to diagonalize the spin orbit, okay? So I need to do some approximation to diagonalize this spin orbit. So the spin orbit, spin orbit is atomic spin orbit. So the potential close to the atoms is roughly spherical symmetric. So I can approximate this potential like spherically, then the gradient that is here in this equation of the potential can be written in this form. Okay. So of course, the potential is not really spherical because it's periodic and so on. But this interaction will be strong only close to the atom. So I can actually, and close to the atoms, I can approximate it like periodic, like a spherical. Okay. So if V naught have a spherical symmetry, then the gradient I can rewrite it in this form. And then you see I get here R cross P, this is the orbital angular momentum, and the spin. So I get this dot product between orbital angular momentum and spin. And all this in, 1 h bar over 4 mc square, and the derivative of V naught, which I don't know because I don't know what V naught is, I just put in a parameter. This parameter would be my lambda here, okay? Now I can use the total angular momentum to rewrite this L dot S in terms of this total angular momentum. So the total angular momentum is the sum of them, and I square them. So I will get this expression here. I can solve for L dot S and rewrite L dot S in terms of the difference of these squares of different angular momentum. Okay. So what is nice here is that, well, in this, if I can choose then like my states for UN naught, a state that are eigenstate of J squared, and then if it is the case, then, well, they will also be eigenstate of L squared and S squared, so meaning I can trivially calculate what it is. It's just a combination of the different quantum numbers you have. Okay. That is the idea. So essentially, you will get that this spin orbit coupling will be given by this expression here. The J is the total angular momentum quantum number, L the orbital angular momentum quantum number, and it's the spin. So for our case, S is just 1/2 because we're talking about the spin 1/2. And L will be 0 and 1 because we saw that these relevant bands are S-like and P-type. So L is equal to 0 for S bands or S states, and equal 1 for P states. Sorry? Lambda is a parameter. I don't know what it is. Okay? I will put this parameter after all in another parameter that can be measured easily experimental. Okay? But for now, it's a parameter. It's a price I have to pay. So I don't want to go into all the detail. I have to pay a price for that. Okay? All right. So I can write then my basis will be the eigenstates of state that transform like the eigenstate of this of G squared, of the total angular momentum square. And this basis, so you can write it. It depends on all these quantum numbers, Ls, J, and Mj. I will simplify the notation just to A and Mj because, well, L and S, I know that is 1/2, so I don't have to repeat 1/2 for all of this. We're talking about electrons. And L could be 0 or 1, so I just will say, okay, if it's conduction or if it's S-band, I just have L equals 0, and I will say it's just S-band without writing the value of L, so I just, the relevant number that I will be using as J and J. Okay. So this is essentially how you can write the states in terms of this basis. So again, so this number here corresponds to J, the total quantum number, total momentum quantum number, in that case is 1/2, Mj is 1/2 also. So we have different combination of this J and Mj, and this doublet is for the conduction band, so it's L equals 0. So these two states here are the states corresponding to L equals 0, S equal 1/2, and then this one, J equal 1/2, Mj equal 1/2, J equal 1/2 and J equal minus 1/2. Okay. And so for one, I will have for a spin up and for a spin down for 1/2 and minus 1. All right, so I can do this for all the other states, combinations for L equals 0 and L equals 1. So for L equals 0, I have these 2 states here, and for L equals 1, I have the other 6 states for forming this quadruplet, is a p-like band, and then another 2, this doublet, which is also a p-like. So, and here is, I have expressed here in terms of this function that are formed like spherical harmonics, but I can also express it in terms of the Cartesian orbitals. Okay, that is more or less the idea. So I now have the basis, and what I can do is then calculate the eigenvalues of this Hamiltonian. Okay, which now is trivial because I know for each of these combinations that I know the values of L, S, Mj, and so I just can go back here and put it in this expression here, and I will get what is H. So of course, in terms of this lambda, which is a parameter. And here are the matrix elements. So I calculate the matrix elements of the of H naught. H naught is the kinetic part plus the periodic potential. And I don't know, because I don't know the periodic potential, so I don't know what are the eigenvalues of that. So I will put in some parameters for them. Okay? So for the S state, I will put, I have the 2 S states, ES, ES, and for the P state, I will just put EP. What are these values? I don't know. I will figure it out later on. So they are parameters. So for the spin orbit, so that's what you get, for that formula when you start to do the combination of all the corresponding L, M, L, S, J, and Mj. So it just will give you expression for the energies of each of these states, and this is the result. So it's a diagonal matrix that depends on this lambda. I want to get my zero of the energy at the bottom of the conduction band, so I just will subtract this energy of the S state, right? So that's what I'm doing here. And then I can write these matrix elements, which is essentially this representation of this Hamiltonian, which is now 8 by 8, at the gamma point for the value k equals 0, okay? I get this diagonal matrix with all these values, okay? And you see these values are clearly 0. So 0, 0, 0, these are the states, this spin up, spin down state, which are degenerate in this conduction band. Then I have minus E naught, I have these 1, 2, 3, 4 states, which are this heavy hole and light hole, right? And then I have minus E naught minus delta, which will give me this green band. Now, so I don't know what are these values because these are parameters, this E naught. So E naught is essentially this, this difference between S naught and EP naught and lambda, and delta naught is given in lambda. So I don't know lambda, I don't know ES, I don't know EP, right? But I can rewrite everything in terms of E naught and delta naught. And I don't know what is E naught and delta naught, but I can get it experimentally. Because I just can put light and look at the absorption, at which energy I will have absorption of electrons that are here in this band that will jump into the conduction band. So I will see this peak, I will see at which energy this peak is happening. So I will measure this energy, which is essentially the gap. You notice the energy gap. And I can do the same for the SO band and then determine what delta naught is, right? So I start with some parameter, I have no clue what it is, but I was able to put this in terms of things that I can then measure from the experiment. So I can measure this in the experiment and for each material and get these values for each material. So I make my table, I have all these values for playing these materials. You want to do calculation, you just have to put these values in your model, okay? That is, now, I know only the dispersion of k equals 0. right? Because I choose this point. Now what I'm going to do is I will use this basis that I use for k equals 0 and rewrite the Hamiltonian at finite k in that basis. So it will give me another A by A Hamiltonian, which then I will have to diagonalize to get the eigenvalues. Okay? So these are the matrix elements at k different from 0. So I will have this extra term, right? So if you look at what we had before, we have this k dot p term, and we have also this term that, this other term. All of these were 0 before, but now they are not 0. So I have to take it into account here. And this m that I'm using here, m prime, is this basis that I use for the case of k equals 0. Okay? Now, so I can get here this m prime, so the states are orthogonal, so this will give me just a delta, Kronecker delta. This term, I will neglect this term because, well, it's of the order of 1 over c squared. It's going to be very small. So it means this term, I already evaluated this for the case, because there is no k here. It's the same like before. This is trivial because I have the delta function here. So I just need to figure out what are the matrix elements of the momentum of P. If I know the matrix element of the momentum, then I just put it in my Hamiltonian, build my Hamiltonian, and I have to diagonalize this Hamiltonian to get the eigenstate at any k in that case. And any k, I mean k is close to 0, because if it's away from 0, I will have to, to use this other approximation. Now, so I don't know exactly what these x are, because the only thing I know is how they transform, how is the symmetry of these states. So I cannot calculate exactly what are these matrix elements. What I can say is when these matrix elements are 0 or not because of symmetry, and which of these matrix elements should be equal to each other. Okay? That is the only thing I can do. But this is enough, actually, for getting things. So, for example, if you look at this matrix element of S, Px, and S, you can see that this is going to be 0 because the S states are even in X, but Px is odd. So when you this matrix element, or the element that you have inside the integral, so S, P, and S, will give you a function that is odd in X. So when you integrate from minus infinity to infinity, you just will get 0 because the function is odd. Okay. So you can figure out also that that these ones, SPXX and SPYY and SPCZ, all of them are going to be equal to some parameter different from 0. I don't know what is the value. Conveniently, I wrote it like this: m naught, so the electron mass divided by h bar, and p naught is some parameter. Okay. So after that, so when I just, I can figure it out also for all the, just put this example, but I can do it for all the combination of these momentum matrix elements. And then I can build this, I can build the Hamiltonian. So the Hamiltonian is an A by A Hamiltonian and can be written in block form, like here. So we have here a matrix. This is 2 by 2 because we have two states in the conduction band. This HB is a matrix which is 6 by 6 because we have 6 states in the valence band. And then we have these 2 times 6 at 6 times 2, which are the coupling between the conduction and valence band. Okay. So what are the values of these Hamiltonians? They are written here. So it's a long calculation to get it there. It's easy calculation, but it's a little bit long because there are many terms and so on. We'll have to be careful in that. Well, that's what I get actually here. This is with magnetic field and everything is in there. And B is some electric potential or whatever you have in there. So that's what you get for this block here, HC. Is this 2 by 2 Hamiltonian. And you see you have here the kinetic energy, you have the potential, you have the Siemens splitting, right? So it just looks like the Pauli Hamiltonian. Then we have this valence band Hamiltonian that we have this form in which this I32 and I12 matrices are like here, and this IB matrix is given by this. And then you have the other coupling part of the Hamiltonian, this 2/6 and C/2, which will be the Hermitian conjugate of this one. So you get a big Hamiltonian. It's 8/8. You see a lot of terms in there. It looks very complicated, right? So you can do it numerically, no problem. But I don't want to do numerics. I want to do something easy. So how to proceed with this? Well, I will want to decouple this band so that I can find a Hamiltonian, a small Hamiltonian just for my conduction band electrons. So I have two bands. In this two conduction band, I want to find a Hamiltonian that is 2/2 that effectively describes this electron, this state, without taking care of the other. Okay. So essentially, what I need is, starting with this 8/8 Hamiltonian, I need to do something to transform this Hamiltonian in some block diagonal Hamiltonian, in which I can decouple now the conduction band state from the valence band state. That is the idea. So, by the way, this is called this K.P model, specifically for this case, called the Kane model. Kane is the name of the person that introduced this model. And this is 8/8, but there is also a 14/14 K model. So you want to complicate more your life. So the idea now is that I will do some unitary transformation to make this done. So I will do an unitary transformation and transform my 8/8 Hamiltonian into this block diagonal Hamiltonian, okay, into this one. I cannot do this exactly. It's an approximation. So when I do this unitary transformation, then my Hamiltonian will transform into this. I will have some AC effectives, which is just transformed, and here also the transform block and the transform block. So now for this unitary transformation, I will use a transformation of the form e to the s, and s have to be written in this form with m Hermitian in order for u to be unitary. So m is a matrix. I don't know what it is. Okay, I just will do a transformation, and I will choose m in such a way that these off-diagonal terms are approximately 0. Okay. So in order to find this transform matrix, so you can expand the exponential functions, and this is approximately to this series of commutators. Okay. So what is the idea here? So I just will put this M matrix here with my H, which is this Hamiltonian here. We calculate the commutators and so on, and this will give me again an 8/8 Hamiltonian, and I will choose M in such a way that these off-diagonal terms or blocks goes to 0 or approximately to 0. So in the lowest order approximation, what you will find, actually this M is given by these matrices, HB to the minus HB to the minus 1, and then HBC. Which then results, and you put the, in this expansion here, you put this M then, and you get to the lowest order, and you get this expression. So this actually, this technique is called downfolding, because you see, you start with your 8/8 Hamiltonian, and it's essentially, it's like this. You have 4 blocks here, and essentially what you are doing is this, your Hamiltonian, and this is downfolding so that you get with, your small Hamiltonian. And so you can do this technique for finding effective Hamiltonian in many cases, in proximity effects and name it. Okay, so this then is a 2/2 Hamiltonian, because AC is 2/2, and this also matrix multiplication will give you a 2/2 Hamiltonian. And if you do the calculation, we know all this. No, remember we have expression for all these, for all these blocks, these matrices. We just need to do this matrix multiplication. We need to be careful there, because some we have momentum in there, so they may not commute with other stuff. So, but if you do that carefully, that's what you are going to get at the end for this effective Hamiltonian. This expression here. Now you see this first part looks like a kinetic term, like p squared over 2m, right? So this pi here is just p minus EA, the vector potential. So it's the the canonical momentum. Okay? So then this term here will looks like a little bit like 1 over the mass. And this is the way we define this effective mass. So now we don't have just 1 over m naught, which is the mass of the electron when it is free. The electron is not free now, it's in this material, so it actually acquired this other contribution here, and the mass gets renormalized, so you get a new mass for these electrons, or quasi-electron. We call it the effective mass, and it's given by this term here. And as I mentioned before, we can measure E naught and delta naught from absorption experiment, but this value of P naught, which is related to the momentum matrix element, you can also get it from the strength of the absorption. So if you calculate the formula for this, the strength of the absorption of the so-called oscillator strength of this absorption is actually proportional to this P naught. You can also find P naught from the experiment. So now we know delta naught, we know E naught and P naught from the experiment. We can put in there, we can calculate what is the effective mass for this material. Okay. So something similar happened to this part of the Zeeman term. So instead of just the G factor for the free electrons, we get a renormalized G factor. We call it the effective G factor. We use this star for this. So we can also calculate now the G factor of the materials if we know what are the parameters P naught, E naught, and delta naught. Okay. That is the idea. So we can calculate these values from the parameters here. I'm actually listing some of these set of parameters for many of these compounds. Some of the values are from experiments, some of the values are from first principle calculations. Okay? So you can also do a theory taking into account everything and try to calculate things. Okay. Now, in all this story, okay, let me make a couple of remarks before going to the case in which we have position-dependent potentials. So, for the typical values of the effective mass, so you will find that for these semiconductors, it's typically much smaller than the free electron mass. So, let's say for gallium arsenide, it's going to be like 0.065. For I think for indium arsenide, it's like 0.3 or something like that. So it's much smaller than the free electron mass. The G factor range, it could be, from values a little bit smaller than 1 or smaller than 2. The two values that can reach actually up to tens of up to 10. So let's say I think for indium antimonide you can get even like 40, 50 G factor, which is like 25 larger than what you have for a free electron. So meaning that then for these materials you can, you don't need this huge magnetic field to have an impact because the G factor now is considerably large. So for the electron, if the G factor is 2, you need a very large field. But if your G factor now is 50, well, you can have an effect even with smaller fields, magnetic fields. Okay. All right, so this analysis was done for the case in which all the potentials are constant. So, but now let's say that my parameters are not constant. Let's say that I don't have just a material, but I may combine 2 materials or 3 materials. I can make heterostructures with different layers of different materials. So then these parameters are not constant. And the potentials or the electric fields, if I put an external electric field, may also not be constant. The magnetic field, if I make it not constant, is going to depend on position. So all the things are going to depend on positions. And now I have to be really, really very careful calculating these terms here if all the things depend. Because as I mentioned before, we have momentum operators in there, and momentum doesn't commute with anything that have position in there. So we have to calculate this carefully. Okay? What happened in this case? I will show you what happened, what are the results in this case, but then the idea is the following. So it's to use the so-called envelope function approximation. So here is a picture. Here on the left, you have a picture of a situation, let's say, in which you have, let's say, a change of atoms, and these are, the potential, attractive potential of these atoms acting on the electron. So this is periodic, is the potential. And if you look at this periodic part of the Bloch function, it will look like this a little bit. So it's mostly localized here where the atom is, and rapidly oscillating. Okay, so it's going to be periodic because, well, the potential is periodic, so it's periodic. But let's say now that you put some electric field or whatever that is modulating the total field. So you have now the field of the atoms, and let's say that you have an external field, electric field, or electric potential, VR, which let's say they have this form. Okay? This is just for illustration. So what is going to happen? Well, the on-site, the total field, electric field at each point is going to change. It's not going to be periodic anymore because, well, your potential is not periodic also, the external potential. So the periodic part of the Bloch functions are not going to be periodic anymore, so they will be modulated with an envelope function. This envelope function, what I call F, modulates the amplitude of these oscillations of the periodic part of the Bloch function. So the idea, because I know what the Bloch functions are, I calculated this for the case that I don't have this potential. So I can use the same basis like before, but now what I will have these envelope functions. And this is what I would like to, what I would get is then not an equation before for U, so I will have an equation for Fn. I know already what U do. And for this, essentially, you do it by expanding the Bloch functions in series of the Bloch function at k equals 0. This is at final k, this is at k equals 0. And now I'm putting here this envelope function, okay, which I don't know what it is. It's what I want to calculate. So the total wave function, then you can write it this, and you can absorb all these coefficients here into just one f. And now we do exactly the same. We build the matrix element of this Hamiltonian using this basis. And you do, again, the matrix representation, the downfolding, and so on. The same thing we did before, but now with this, starting with this wave function. And finally, what you will get is this equation here, which is pretty similar to what we had before. The difference is now that since the parameters are changing are position dependent, so the effective mass is also position dependent, and it appears here in this, inside this, and it makes sense. I cannot get it out here because I cannot write. You see, before I have this term for the kinetic energy, but m is now position dependent. If I put m here, well, this is not Hermitian because P and M don't commute. And it's, from the calculation itself, what you get is actually this. And this happens to be actually Hermitian. This is okay. All right, so then you get something similar for the, this is the external potential. You get something similar for the Zeeman, but now, well, your G factor also depends on position, because also the parameters depends on position if you have different materials, okay? And the important thing is that you get here this extra term, which essentially comes from this, from this matrix element in which you have the momentum, and there are things that don't commute, then you get this term, okay? So the effective mass, the relation for the effective mass and the G factor are exactly the same like we had before, but now, okay, we have also this electrostatic field, which we have to put it here, and all the things depends on position, so I explicitly wrote here this position dependent. And we get this, this extra term, which is like an effective spin-orbit coupling, in which you have the gradient of this function, which depends also on the position dependence of these parameters describing the system. Now, there is a huge difference between this one and the one that we neglected. We neglected the spin-orbit coupling, this atomic spin-orbit coupling, which was proportional 1 over c squared. There is no 1 over c squared here in this one. So this is not going to be small, or at least not small like the other one. Okay. And the amplitude also actually depends on, what are these parameters. So this term is going to get us some spin, it will help to break the spin degeneracy, even if you don't have magnetic field. And here is an analysis a little bit of how to break this spin degeneracy. And let's say that you have time reversal symmetry in your system. So you have a state, time reversal will change k to minus k and will flip the spin. Okay? If you have this symmetry, time reversal symmetry, then the energy should not change under this transformation. So the energy at k for a spin up should be the same like the energy at minus k for a spin down, right? Now you have inversion symmetry. Inversion symmetry just change k by minus k. So if your system have this symmetry, then the energy at k with the spin up should be equal to the energy at minus k with the spin up, and the energy at k with the spin down should be equal to the energy at minus k with the spin down. So if you combine these two symmetry, so you just substitute this equation in here, you will get that the spectrum must be degenerate, spin degenerate. So E k up have to be the same like E k down. So the spectrum is degenerate. So you want to break this spin degeneracy, means you have to break these two conditions. One way is to break time reversal symmetry, and this you can do it, let's say, by applying a magnetic field. And the other, which is more subtle, is to break the inversion symmetry. So if you break this inversion symmetry, then this is also, the spin degeneracy is also broken. We can break the inversion symmetry by using the appropriate material. So we discussed at the beginning this thin plane crystal, in which they don't have an inversion symmetry. So in this material, you will have, the spin degeneracy will be broken because they don't have a point of inversion symmetry. These are called non-centrosymmetric materials. Or we can design structures that are non-symmetric in order to have also spin degeneracy broken. And ultimately, of course, we can have both things, magnetic field, break both, time reversal and inversion symmetry. Any question? Yeah. Okay. All right. So how to break the inversion symmetry? If apart from this inversion symmetry that you have from the structure of the material itself, you may also break the inversion symmetry by engineering your structure. Okay. So you may have inversion symmetry or the lack of inversion symmetry or structural inversion asymmetry is typically what it's called, SIA. Let's say at a surface, you look at the z direction. So what you have above the surface, maybe it's just vacuum, is different when you have below. So the inversion symmetry with respect to the z direction is broken in this case, right? So then you may have states at this surface which will have broken spin degeneracy. Okay, you will have essentially some effective spin-orbit coupling at these surface states. But it could happen also at interface. So you will have two different materials, so the interface between them is also breaking the inversion symmetry, and then you will have a corresponding spin-orbit coupling and broken spin degeneracy. Or you can, form this different stack, different combination of material. You just have to break somehow the inversion symmetry. Okay, so you can engineer that. So the simplest example is what I'm going to consider now, and this will give you something that is called, it's a simple model for the so-called Rajah spin-orbit coupling, which is very popular in spintronics. I think one of the most popular things in spintronics is this rational spin-orbit coupling. Okay. So we have this expression. Suppose now we have just just a couple of layers. So like in this case. And if we look at the profile of this conduction band, let's say in one material maybe like along the Z direction. So it may look like this, like we have here. Okay, so let's say that this is the conduction band here of material A, and here we have the conduction band of material B. But if I have doping, so it's going to bend, so I can have a situation with this profile of the electric field across the heterostructure looks like this. Okay, so I can have a so-called two-dimensional electron gas form here. So you see this form here like a quantum well in this region, and I can have states confined in this region. So there is confinement here in the Z direction. So the Z direction is in this direction, and the system is invariant in the planes or in the XY direction. It's like a 2D system. So this is just the side view of the system. So in the Z direction you have confinement, XY electrons are free to move. So it's a two-dimensional electron gas. It's two-dimensional because, well, the electrons are allowed, they are confined inside this well, and I just allowed to move in this plane, forming this quantum well, okay? Now, in this situation, so the parameters doesn't change along X and Y because along X and Y have the same material. They change only on the Z direction, because on the Z direction I can go from material A to material B, and I also have this potential here that depends on Z. So the function lambda, what we have in this spin orbit coupling before, depends now only on Z. Okay, we take this form approximately. So the spin orbit coupling induced by this lack of inversion symmetry, which we found that is given by this expression here. Sorry, here is missing the dot sigma here. So this should be here dot sigma. I will correct it in the slides later on. And so the gradient, essentially will depend only on C, so you will get this expression here. Okay? Well, again, so this lambda I can calculate it because I know the potentials, the values of E naught, D naught in the different materials. So. But let's have a look at this quantum well. So in the quantum well, so that's the equation that we have now. So we have this equation. I ignore now magnetic field, no magnetic field, so I don't have pi, I just have P here. B is this conduction, this electric field of the bands. This alpha over H is just this delta lambda, okay? Delta lambda, or the derivative of lambda over C. I just recall it here. Alpha depends on C. Now this is, I have a potential. This potential is the quantum well potential in the Z direction. In the X and Y direction, the system is free. So I can decompose or propose this function as the product of the function that gives me the confinement and plane waves in the X and Y direction, right? So if I do that, so all these Py and Px just will go to Ky and Kx because they are plane waves and the momentum is conserved in the X and Y direction. So you will get essentially this equation here. Okay, and what is alpha and what is m in here? So 1 over m is going to be this, essentially the average of the 1 over the mass. The mass is changing from material to material. So you have this dependent on the mass. And F is the electronic state of this quantum well. So it's the average, essentially, of 1 over m. And alpha is the average of this delta lambda over delta C. So this is exactly what is called the rational spin orbit coupling. And the parameter that describes the strain of this is this alpha parameter. So one thing is important to note here is that alpha is going to be 0 as long as you have inversion asymmetry. If the system is inversion symmetric, alpha is going to be 0, so you won't have this spin orbit. Okay? And you can see this just from symmetry. So if the quantum well is symmetric, then the wave function of the quantum well are either symmetric or antisymmetric. So you have this relation, f of c is equal plus minus f of minus c, either plus or either minus. Then lambda c is the same like lambda minus c because, well, it's symmetric, the well that the first derivative is then antisymmetric. And when you put all of this, what you get in the integral is something that is antisymmetric. So when you integrate it, it just goes to 0. So if the quantum well is symmetric, alpha is 0, so you don't get anything. In order to get a finite spin orbit coupling, you need this quantum well to be asymmetric. Now the nice thing here is that actually you can control the values of the alpha, because you see the alpha depends on this average value, and I can change the probability density. I can change the density corresponding to these states in the quantum well and push the wave function to be more on one side or the other, so I can pick more on the difference of the parameters in the two materials or less. So I can change the value of alpha just by pushing the electrons to go to one side or the other. And let me see. Okay, so let's say I have this is my quantum well here, so let's say the wave function is somewhere here. I can put an electric field that push the electron a little bit to the other side, so let's say here. And then they will pick more this high electric field here, okay? So the alpha will be stronger. I can push them less, and then the alpha will be smaller. So I can control the amplitude of this spin orbit coupling electrically. And this is a huge thing for spintronics, because then you don't need to use, or you don't need to rely so much in magnetism or magnetic fields. You can control the spin electrically. Okay. That is all the story. Now we have this Hamiltonian, and so finally I will just want to show how this band looks like now when you have a spin orbit coupling. And so they look like this. So these are the bands. So you have two bands, one for one spin chirality. I cannot say now spin up, spin down, because, well, spin orbit coupling doesn't conserve a spin. So I don't have the spin essentially here locked to the direction of the momentum for each band. Okay. So we have, if you look at this Fermi contour, so if I cross the energy dispersion at the Fermi energy, you get these contours here. And the spin, so these arrows here denote, or actually are showing the direction of the spin at, for each k direction. So you have one band in which you have a chirality, the spin is actually going that way, and the other band, the spin is going the other way around. Okay. So here the chirality is not conserved, so you can actually go from one band to the other by flipping a spin. There are some materials in which actually you get something like that, but you get one of these contours in one surface, and one of the chirality in one surface and one of the chirality in the other surface. So in each of these surfaces, then the spin, the chirality is conserved for these materials. So these are the so-called three-dimensional topological insulators. So typical values for this alpha in millielectron volt angstrom for gallium arsenide is small, is 5. But for indium arsenide and indium antimonide is large, 110, 530 millielectron volt angstrom. Right, so just to conclude a little bit, a comparison between what happens when you have exchange field or magnetic field and when you have rational spin orbit coupling. So you can see this like a shifting of the bands horizontally for the case of Rajwa, and vertically for the case of exchange, splitting, or magnetic field. So let's say that we start with my band in the absence of a spin-orbit coupling and magnetic field. So let's say B is 0, spin-orbit coupling is 0. Okay. So these are my two bands. They are spin degenerates, up and down. Okay. So one over the top. So spin up and spin down band are one on the top of each other. What happens if I apply a magnetic field? So, or I have a change field. So we saw that they split. So one of these bands goes up and the other goes down. So this will be a situation, let's say B different from 0. And when I say B, well, it's the same like you have a change field, right? So it's, in this model, it's the same. And let's say that I have alpha equals 0 here. So only magnetic field. So the bands, so one of them shift up. So if I have my original band here, so one shifts up, the other shifts down. Okay, let's say that this is spin up down, and then this is. Okay. So what happens now if I have B equals 0, but alpha is different from 0? So here the band shift vertically, one up and down and down. In that case, they will shift horizontally, one to the left, one to the right. So, and I will end up with something like this. Okay, so this is essentially, you see these two paraboloids. One paraboloid is from here, okay, from this, and the other here. All right. So what happens if you have both of them? So I now have B different from 0, and alpha different from 0. So what happens is, well, I will have something similar to that, but I will open a gap here, okay? Because the magnetic field will, open a gap at k equals 0, so I will end up with something like this. Okay, so here I just open a gap. Okay, so any question? Yes?
If the alpha is not equal to 0, that means the two band is shifting vertically, horizontally. Then why the spin? Why the spin is different? Like for the inner circle and the outer circle, like if you consider like if one spin is spin up and one is spin down, maybe.
Yeah, I cannot say what is spin up and spin down when I have a spin orbit coupling.
Okay.
Spin is not conserved, so there is no spin up and spin down. I have just chirality. I can say when I rotate in the K space, one is going to be clockwise, the other counterclockwise, changing, like you can see here.
Okay.
But there is no, spin is not a good one to number, so I cannot say what is happening. Any further question? Okay, so with this I will conclude the lecture for today, and next week so we will continue a little bit, talk about another kind of spin-orbit coupling, and also some applications like tunneling, magnetic resistance. I think it's the next step. Yeah.
Okay, so I will try to get the lectures and upload them to my Moodle. You can download them and I just want to say that all these calculations, which were all these approximations, the people developed them in 60s, 70s, because that time there was not any DFT. So it was basically like cooking with a simple ingredient and just put some many parameters and try to get them from the experimental data, like absorption and transfer. But nowadays, like Raj, they are able to calculate them from the first principles. But that was like the story. But at the end, we are just dealing with 2x2 Hamiltonian.
So I can say that if you look at this article, because, everything is so, all the expressions are very large and so on. And if you look at different papers, you will always find a lot of misprints. And when I was writing this review on Spintronic, it was tough, so I could not really copy many of things because I didn't know which expression was correct or not, because they will change from one paper to another, because it was very likely to make mistakes writing things. So I actually spent a lot of time writing all this from scratch myself. And ultimately, I made the same mistake. So you look at this, there are some misprints also there. It's just unavoidable to so many expressions so long that you will make mistakes writing down.
And we just do the first order perturbation theory, or maybe second, but I have a friend who did it to the fourth order. So these formulas for the effective mass, there are other terms if you do the approximation to higher order.
Yeah, we also were in hurry with this for this review, so not much time.
Okay.
Anyway, yeah.